Today we're going to start covering Chapter 25 on electric circuits, and we'll spend 2 class periods on this material. So I want to start with a question. The question is, a wire is connected across a battery. How much current will flow through the battery? So let's just imagine what we're talking about here. We're putting a wire like that, and let's just say that our wire has a resistance of 0.01 ohms. And it's a standard 1.5 volt battery, so V is 1.5 volts. And if we go ahead and calculate the current using Ohm's law, current is voltage divided by resistance, we would get that the current in this situation is 150 amps. And my question for you is, really? Do we really think that a little 1.5 volt battery, like even a D cell battery or AA, AAA, is that battery really going to be able to put out 150 amps of current? And the answer is no. Okay, so we need to figure out a way to model how an actual battery works, because a battery will put out the current that you would calculate with Ohm's law, as long as the resistance is kind of a reasonable higher value. But it's not going to if the resistance is too low. Let's look at another example that shows that. The question is, why do the lights dim in a car while the car is starting? So imagine that we look at the circuit for the headlights in your car. Let's say we've just got 2 headlights. So we've got our 2 light bulbs, and they are connected directly to the battery. Now, when you try to start your car, what you might notice is that the headlights dim when you do that. And if you think about that, that doesn't really make sense, because the starter circuit, in other words, the circuit that's making the starter motor go around, that's a different circuit. It's connected in parallel to the battery. So you would think that what's going on in that circuit would not affect the circuit with the headlights, because different circuits connected in parallel to the battery. However, what actually happens is the starter in the electric starter for your car motor draws a lot of current. And it turns out that what happens when you draw a lot of current from a battery is, even if it's supposed to be a 12 volt battery, the voltage across the terminals is going to go down. So both of these problems indicate that we need a better way to model how a battery actually works. But it's not just a battery. You may have had the experience being in a home or office building where an air conditioner kicks on and there's a momentary dimming of the lights. So this is also true even when we're looking at the electrical power from the power company. All right, so in order to figure out this problem, we have to introduce something new, which is called electromotive force. The most important thing to say about this is that normally nowadays we just call it EMF. We don't call it electromotive force because it's a bad old-fashioned name. EMF is not a force, it's an electric potential difference. And as you look at the slide here, basically what we're saying is that the EMF is something that a battery or an electrical outlet provides in a circuit. So up to this point, I've just been calling the battery voltage V, but now we're going to use E for EMF. And we use the capital cursive letter E to represent EMF. I know that's a little bit confusing because we've got a couple other E's, especially this one, our permittivity of free space, that we want to be careful with, okay? So it's not electric field, it's not the permittivity of free space, it's a new thing called EMF. And so you can see that in this circuit, we're saying that the battery is providing a source of EMF. It's providing the electric potential difference for the circuit. Now, how is this going to help us to understand how a battery or power supply actually works? Well, what we do is we define something called an ideal EMF. An ideal EMF does not exist. Okay, so there's no such thing as an ideal EMF, but what you're going to see in a minute is that it helps us model the actual behavior of a battery. So an ideal EMF is simply a source of electric potential difference that can maintain the same potential no matter what the load is. Now, by the way, the load just refers to the overall resistance that it's connected to. So what we're saying is, even if the load is 0, the EMF stays the same. Another way of saying that is we can imagine that it could put out an infinite amount of current when connected to a 0 resistance. Again, this thing doesn't actually exist, but as we're about to see, it's useful in modeling how an actual battery works. So here's how we model the way that an actual battery works. Here is our battery, and our model for the battery is that it is an ideal source of EMF in series with an internal resistor. Now again, it's not like there's really an ideal EMF and we stick a resistor in series with it. This is simply a model which works very accurately to show how a real battery actually behaves. Okay? So in other words, what you'll notice is that the voltage that actually comes out of the battery, what we call the terminal voltage. So in other words, if I take a voltmeter and I connect to the terminals of the battery, what I measure is the terminal voltage. Well, what the terminal voltage is going to be equal to is it's going to be equal to that ideal EMF minus the voltage that's lost across the resistor. From Ohm's law, that's just I times R internal. Now, how does this help us with understanding what's going on in those examples that I talked about? Well, what you'll notice is that the greater the current that's being drawn from the battery, the less the terminal voltage becomes, because we get a larger voltage drop across that internal resistance. And so that's why when you are, starting your car, the voltage across the battery terminals goes down because you're drawing so much current from it. The other thing this shows us is that even if we do something stupid like connect a wire across the terminals of a battery, the current's not going to be infinite because it's going to be limited by the internal resistance. All right, let's take a look at an example using this formula. And by the way, you might want to pause the video and see if you can get the answer yourself. A 12-volt car battery is providing a current of 12 amps. If the potential difference across the terminals measures 11 volts, what's the internal resistance of the battery? So first of all, in this problem, when we call it a 12-volt car battery, what we're doing there is we are giving the ideal EMF. So E is going to be 12 volts in this problem. The terminal voltage, what we actually measure, V term, just going to write term instead of writing out terminal, is 11 volts. And so now we should be able to take our equation and solve for the internal resistance. So I'm going to take that equation, and if I solve that for internal resistance, I get R internal is equal to the ideal EMF minus the terminal voltage divided by the current. And so if we work that out, when you guys work it out, you should find that the internal resistance of this battery is 0.083 ohms. Now, by the way, again, this is just a model of how a battery works, but one of the things that you find with something like a car battery is that as that battery gets older, the effective internal resistance increases. And that's why at a certain point, when you try to draw enough current to start your car, so much of the voltage is lost internally that your car or the starter is no longer getting enough current to actually turn over and start the motor. In terms of what's the resistance of the load, so in other words, what is the resistance of what's connected to it? Again, this concept of a load just means the total resistance of what you're connecting to the battery. Okay, so to figure that out, what we want to notice is that the voltage that's across our load is the terminal voltage. So since V is equal to IR, the terminal or the current through the resistor we know the terminal voltage. So the resistance of the load would just be equal to the terminal voltage, the voltage it's connected to, divided by the current that's going in the circuit. Remember, in a series circuit, the current is the same everywhere, so we know that the current is 12 amps. And so we get 11 volts divided by 12 amps, or 0.92 ohms. Okay, now that we've learned a little bit about how batteries actually work, the next thing we want to do is we want to look at resistors. And we want to specifically look at how they add in series and parallel. So first of all, remember that a resistor is just a device in a circuit that always has a constant resistance. And when you look at a resistor in a circuit, you'll notice that they look like cylinders and they have little bands on them. And there is a color code for those bands that tells you what the value of the resistor is. If you just Google resistor code, you can take a look at that. Take a look at how that works. Before we talk specifically about resistors, though, I want to remind you about some of the things we've said about series and parallel circuits. This is really important stuff to understand. So first of all, in a series circuit, we know the current is the same everywhere. No matter where I am in the circuit, the current is the same. So if I've got light bulb number 1, light bulb number 2, and light bulb number 3, the current through each of those, so through that filament, each of those is the same. So that's what I mean by I1, I2, and I3. The other thing that we know for a series circuit is that the voltages add. So in other words, the voltage, the terminal voltage that the battery is putting out, is going to be equal to the sum of the voltages across each of the things that we have in series. One of the other important things about series circuits, if you break the circuit anywhere, so if this light bulb burns out, then no current flows through the circuit because there's only one way through. If you break it anywhere, you no longer have a complete circuit. So let's use that information to figure out how resistors add in series. So again, a resistor is just a component that has a fixed resistance. And we've got our two equations here from the last slide. What we're trying to figure out is what is the one resistor that could be used to replace these three resistors such that the current being drawn from the battery would be the same. So what I'm going to do is I'm going to start out with this formula. We know that the voltage, the terminal voltage of the battery, is going to be equal to the voltage across each resistor, but the voltage across each resistor can be written in terms of current and resistance. Again, we're just using Ohm's law. So instead of V, I'm going to write R equivalent times I. And instead of V1, I'm going to write I1 R1. Instead of V2, I'll write I2 R2. And instead of V3, I3 R3. Now, we want to use our second of these relationships to simplify that. We know that the current is the same everywhere, and so all those I's are the same and they just cancel out, and we get that resistors in series add in this very simple way. By the way, one of the things you'll notice is the rules for resistors and capacitors are reversed. Remember, capacitors add in this simple way when they're connected in parallel, but resistors add in this simple way when they're connected in series. Let's look at the parallel situation. So again, some important things to remember about parallel circuits. The terminal voltage that the battery puts out is going to be the same as the voltage across each of our devices that are connected in parallel, because effectively they're all directly connected to the battery. What we find then also is that the current leaving the battery is going to split into those three different branches. And so the current through the three branches together has to equal the current that's coming out of the battery. The other important thing about a parallel circuit is that if one of our light bulbs burns out, it does not affect the other bulbs. In other words, if that filament burns out, the current can still flow through each of the other two bulbs. So one object burning out doesn't affect the others. Okay, let's use these two formulas to figure out how resistors add in parallel. You might guess that it works the same way as capacitors add in series, and you'd be correct. Okay, so in this case, I'm going to first start with this formula. And since we know that in general current is voltage over resistance, I can rewrite that as the voltage of the battery divided by R equivalent. And now I1 would just be V1 over R1. I2 would be V2 over R2. And I3 would be V3 over R3. But, of course, we know that all of the V's represent the same thing, and therefore we can cancel them out, and we get that 1 over R equivalent is equal to 1 over R1 plus 1 over R2 plus 1 over R3. And that's how resistors add when they're connected in parallel. Again, you'll notice that that's how capacitors add in series. All right, let's look at the following problem. So the problems for resistor networks like this are very similar to the problems that we did for capacitors. In other words, I give you a bunch of things connected together. You had to find the equivalent capacitance, and then you had to find the charge on each capacitor and the voltage across each capacitor in the original circuit. Exact same kinds of problems for resistors, and they're done in exactly the same way. And again, as long as you understand the fundamentals of series and parallel circuits, you should be able to do the problem. But if you forget those, then you won't get very far. All right, let's look at this particular problem. We've got 4 resistors, and the first thing to do is just figure out how they're connected. You'll notice that R1 and R2 are in series because once I go into R1, the only place to go after that is R2. You'll also notice that R3 and R4 are connected in series. And so the first thing I'm going to do is I'm going to figure out what is the one resistor that replaces R1 and R2. Because they're in series, that's very straightforward. R12 is just going to be equal to the sum of R1 and R2. And in this case, I can see that that's just 22 ohms. For R3 and R4, same thing, they're connected in series. So R34 is equal to R3 plus R4. And if I do that simple math, I get 27 ohms. Now, just like in the problems that we did involving capacitors, once you've done some combinations, you want to redraw the circuit. So I'm going to redraw the circuit. And by the way, I'm going to draw it in a more standard parallel format. You'll notice that this resistor is what we're now calling R12. And please make sure you use that naming convention that I've been demonstrating, because when I'm trying to grade exams, if you're not using that, I'm not going to be able to figure out what you're doing, and you're not going to get full credit for the problem. Okay, so that's our redrawn circuit. At this point, you'll notice that to get to our one equivalent resistor, all we need to do is to combine those two resistors that are in parallel. So we know how that works. 1 over R equivalent is going to be equal to 1 over R12 plus 1 over R34. Okay? And you might want to just make sure you get that math correct, because what I find is this is a very common issue that students have is they add the 1 over R12 and the 1 over R34. They forget to take the inverse of that to get the answer. So for R equivalent, what I got was 12.12. Now you'll notice I'm keeping a couple extra sig figs in this since it's an intermediary calculation that I'm going to keep using. And if you don't do that, what ends up happening is your voltages and currents don't quite add up to what they're supposed to. So that's why I'm keeping a couple extra significant figures. Okay, once we know the value of Req, you'll notice that we can figure out the current here in the circuit. So let's go ahead and figure that out. The current is going to be V over R equivalent, and that's 6 volts divided by 12.12, and I get 0.495 amps. Again, keeping that extra sig fig for now so that I can really make sure that things sum up the way they should. Okay, so I've answered the first two questions. What's the equivalent resistance of the circuit and how much current is drawn from the battery? Now the next part of the question is going to be to figure out what is the current going through each resistor and what is the voltage across each resistor. So in order to do this, let me just remind you what our circuits are, because just like with capacitor problems, you want to work your way backwards through the circuits. So remember that our first combination was this, that we had R12 and we had R34. Okay, so one of the things that you'll notice is that we know what the voltage is across each of those because they're connected in parallel to the battery. So I'm going to figure out what is the current through each of these branches. I'm going to call the current there I12 and the current there I34. I can see that I12 is equal to the voltage of the battery divided by R12. So that's 6 over 22 ohms. And when I did that, I got 0.273 amps. Now again, I'm keeping that extra sig fig just so I can see how things work out. Okay, let me do the current through I34. So that's R34 dividing into the voltage, so 6 over 27. And what I get for that is 0.222 amps. So I want to show you that right away we can do a check, because remember in our equivalent circuit, what we found was that the current coming from the battery was 0.495 amps. Well, since that current is splitting into I12 and I34, these have to add to 0.495 amps. And we can see that they do. And again, that's why we're keeping those extra sig figs so we can really make sure it works. Okay, so we know those. Now, the next thing you got to remember to solve ultimately what we're trying to find, which is the current and the voltage through each individual resistor, is that when resistors are in series, the current through them is the same as the current through the equivalent resistance. So once I know I12, I know that I1 and I2 are equal to I12. So in other words, the current through resistor 1, the current through resistor 2 are both 0.273 amps. In the same way, I know that the current through I3 and the current through I4 are also the same as the current through their combination, or 0.222 amps. So now I've got the current through each of my resistors. The last thing I'm asked to do is to find the voltage across each resistor. Well, once you know the current and you've got the resistance, that's pretty easy. We know that voltage is equal, I'm going to write it up here because the bottom of the slide doesn't work very well. So V1 is just going to be I1 times R1, and V2, V3, and V4 are going to be the same thing. I'll just tell you what I got. When I did V1, I got 5.46. For V2, I got 0.546. And by the way, these are volts. For V3, I got 5.55, and for V4 I got 0.444. Okay, now what do we know about these voltages? We know that the voltage from here to here has to be 6 volts. So you'll notice that if you add the voltage across this plus this, that should equal 6, and you'll notice it basically does. And if you add the voltage across this plus the voltage across this, that should also equal 6. And within, our sig figs, it does. Okay, so in our online office hours, we'll do another example or two of these. In fact, I'm probably going to post an additional example for you just so you can practice with it. The next thing I want to talk about are 2 rules that, if you ever take an electronics course, will be pretty central to them. They're called Kirchhoff's rules, and they are called the Junction Rule and the Loop Rule. So let's start with the Junction Rule. The Junction Rule basically says something that we've already been saying. It says that the sum of the currents coming into a junction is equal to the sum of the currents going out of the junction. Well, we've already been assuming that. In other words, if, let's say, current 1 and current 2 are coming into this junction, and current 3 and current 4 are going out of the junction, all we're saying is that I1 plus I2 is equal to I3 plus I4. Okay? You'll notice here I wrote down conservation of charge, because fundamentally this is just a result of conservation of charge. If a charge goes in to the junction, it can't disappear there, it's got to come out. Okay? Or if a charge comes out, it couldn't have just been created at the junction, it had to come in. So it's really just a statement of conservation of charge. Let's look at Kirchhoff's other rule, the loop rule. And the loop rule says the sum of the changes in the potential around any closed path of a circuit must be 0. Now, we've been using this also, but you might not remember or might not see why that is. So first of all, let me pick a point in our loop to start, point D, and we're going to come around the circuit in this way. So if we cross a battery from negative to positive, that's a positive voltage. So we're going to call that E for the EMF of that battery. And so the sum of the voltages has to equal 0, is what Kirchhoff's rule says to me. So that means that the first voltage is E, but now I go through this resistor, and I'm going to just call that R1, and I'm going to call this resistor R2. When we go through R1, we get a voltage drop. Okay, so in other words, we get minus IR1. When we go through resistor 2, we get another voltage drop, so that would be I times R2. Again, just using Ohm's law for that. And that has to equal 0. Well, notice that the way I've been saying it is the voltage of the battery is equal to the sum of the voltages across the resistors. Well, really, that just comes from Kirchhoff's loop rule. Okay, so it's really not, again, something that we haven't talked about. The loop rule is really just a statement of conservation of energy. remember that electric potential difference is just energy per charge. So in other words, the battery is what provides energy to the circuit, and then that energy is being used up in the resistors in the circuit. Okay, so it makes sense that whatever energy the battery puts out is equal to the energy used by the two resistors. Well, if we now take that and divide by charge, it still has to be true. And so that's where the loop rule comes from. It's just conservation of energy. I want to talk about this graph and how you would actually generate this graph. So imagine that we have our voltmeter, and we take the black probe and we just connect it at D. And then we take the positive or red probe and we just take it and connect it to different places. So if we connect it at E, then we would measure the voltage of the battery, or 12 volts. So notice here at E, it's showing us the voltage is at 12 volts. If we connect it at point A, we'll notice we haven't lost any voltage along here. We're assuming our wires have basically no resistance. So at A, the difference between D and A is still 12 volts. But now if instead we connected B, you'll notice that we've lost voltage across R1. And so that amount of voltage that we lose is just the current times R1. And so this is what the voltage would be at point B. Now, if we connect at point C, you'll notice we've now lost the rest of the voltage across R2. And so the potential difference between C and D is 0. And so from C to D is 0. If we go back to E, we're back up on the top. So that's kind of an example showing you how we could think about a circuit with Kirchhoff's loop rule and with a voltmeter. By the way, key thing to remember. Remember, the current is the same everywhere in the circuit. The thing that you lose as you go around a circuit is the voltage. So you can be pretty sure there are going to be some multiple choice questions on the exam that make sure you know that in a series circuit, the current is the same everywhere, but as you go around the circuit, you lose voltage. The last thing that I want to talk about today related to what we've covered is how you connect an ammeter and a voltmeter. So one section actually got to do this in practice. Unfortunately, the other section you just got to do a simulation. But the key thing to know about ammeters, and by the way, an ammeter measures current, ammeters are always connected in series. You have to actually remove a wire from the original circuit to connect an ammeter. So you'll notice here, we just have this one wire going from here to here. We got to remove that to connect our ammeter. So ammeters are connected in series. Now, ideally, we don't want our measuring instruments to affect what we're measuring. So you'll notice that ideally an ammeter would have a 0 resistance, because if it's got resistance, then by putting it in the circuit, I've changed the resistance of the circuit. In practice, ammeters do have very low resistances. And that's why this is true, can be damaged if connected in parallel by mistake. If you take an ammeter and you do this, connect it across a battery, you will immediately blow out the ammeter because it has so little resistance, it tries to draw way too much current. Now, ammeters do have a fuse in series inside the ammeter, so that hopefully that fuse blows in time to protect the electronics. But my experience is that it doesn't always blow in time. If you connect an ammeter to a high, to like a 12-volt car battery in parallel, you're probably going to ruin your ammeter. Okay, if we look at how voltmeters connect, remember that we want the current through a circuit, but we want the voltage across a circuit. And so voltmeters are always connected in parallel. You'll notice if I want to measure the voltage across resistor R1, I can just take my voltmeter and connect it across that resistor. So I don't have to change the original circuit in any way. Now, again, we don't want our measuring instrument to affect our measurements. So the current that's coming up here, we basically want all of that current to go through R1 and almost none of it to go through the voltmeter, ideally none at all. Well, of course, a little bit has to. But in order to get very little current to go through V, that means we want it to have a very high resistance, ideally infinite, but just big. Those the digital voltmeters that we have in the lab, they've got a resistance of about 10 to the 6th ohms. Okay, so 1,000,000 ohms, that's a pretty high resistance and works well. You can imagine if resistor R1 is 10 ohms, then a very small fraction of the current is going to go through a resistance of 10 to the 6th ohms instead of going through 10 ohms. Okay, so that's an important thing to remember when you're connecting meters, that ammeters connect in series, voltmeters connect in parallel. All right, that does it for today. In our next class, we'll be looking at RC circuits.